Hi everyone, it's Eleonora. Today we're going to make this fun little shader that takes a flat surface and gives the illusion that it's a sphere. I think everyone likes how cute this looks in Animal Crossing and makes the world so much more unique. So let's get started so you can add this effect to your games too. If you're enjoying my videos, consider subscribing, like and share if you find this useful, and there's also a Discord server where you can come and hang out with us as well. So without further ado, let's get started. So I'm gonna save myself some time and import Jamo. It's a 3D character that Mix and Jam kindly provides for free. And I'm also gonna import this very cute low poly plant pack so we have some stuff in our scene. Now I just have the demo scene of Jamo open and I want to show you something here. What we're going to do with the shader today is we're gonna loop through each vertex of the object that we are applying the shader to. And for each vertex, we will want to change where that vertex appears on the screen, depending on how far away from the camera it is. But if we look at the wireframe of the cubes used in this scene, they have a very low number of vertices. They only have vertices at the corners. So if we were to try to apply our shader to an object like that, we won't end up with a curve, simply because there are no vertices between the edges. So let's remove these cubes and swap them for a plane, since planes have a lot more vertices. And I'm gonna scale this and I'm gonna add a texture just for aesthetics. This is a texture I also downloaded from the asset store and just tinted it to match the character. And I'm just gonna add some trees around as well, and this is what we're gonna start with. Now let's create a new surface shader. Just right click, shader, surface shader. I'm naming this round world. Now let's apply our shader to everything in the scene. Let's open the shader up. Now to be able to add our custom vertex modification function, we have to define it in the pragma by saying vertex colon the name of our function. So let's name that vert. And now if we scroll down and add the function, so void vert, and that takes a variable in-out app data full v, and v is the name of the variable. And you can also use app data underscore base or app data underscore tan, depending on what you will need to use within the function. So that's just going to give you access to a different amount of information. From the Unity documentation, app data base will give you position, normal, and one texture coordinate. App data tan, position, tangent, normal, and one texture coordinate. And app data full, which is what we're using, and will give you position, tangent, normal, 4 texture coordinates on color. So in here, Unity will loop through all the vertices of the object and it will do whatever we tell it to do for each one of them. So first thing we want is to get the vertex position in world space, since what we get by default is an object space. And Unity provides us with a multiplication matrix to do this. So all we need to do this is float for distance equals, and then we use the mul function, multiplication, and Unity object to world, and then comma v.vertex. I'm naming this distance because I'm going to reuse this variable so I don't define another one, but this is just the vertex position in world space. The second thing we will need is the distance between the vertex position and the camera position. And again, we have this provided for us as well, so let's do distance minus equals world space camera pause dot xyz. Now let's move to our whiteboard so we can figure out what exactly we can do. We have the distance from the camera on all 3 axes, x, y, z. We don't care about the y-axis, which in Unity is the height. We want the curve of the ground to be the same regardless of how high up the camera is at different times. We want to have a curve at the horizon behind the character. So we have the bend of the plane behind the character. Therefore, we are interested in the depth, which in Unity is the z-axis. So the further back something is compared to the camera, the lower we want it to go, basically. And if we want to do the same to the sides so it gives that feeling of a sphere, then we will also care about the x-axis and check how far to the left or how far to the right something is from the camera. But for now, let's just look at the depth. Let's plot it this way. We have the z-axis here, And then we have the y-axis here, which is the height. And we're just gonna ignore the x-axis for now. So let's pick a random vertex, and let's say that vertex is a depth 5 and a height 3. And let's also place a camera at, I don't know, let's say 10 and 5. Let's add one more random vertex for comparison. Let's say again at height 3, but at depth 7. So that's the perfect example, because these two now are the same height, even though one is 3 units away from the camera and the other is 5 units away from the camera. We want the height to exponentially decrease with distance. And here we can really use any exponential formula we see fit, really. Let's look at some graphs. This is the graph of x squared, and as you can see, it exponentially grows, but we need something that exponentially decreases. So let's look at the graph of minus x squared. So that seems like it fits what we were trying to do, but really any formula that exponentially decreases would produce a very similar effect. Let's just quickly plug in this in our example to see. So this vertex currently is height 3, so let's subtract from it 5 squared, so that's minus 22. And this one would be minus 6. So that's a pretty big difference, but it's indeed higher than the vertex further back. If we take another one, even closer to the camera, let's say it's at 9, so this is just 1 unit away. That would be 3 minus 1, which is 2, so even higher. So you can see the exponentiality, is this a word, in action. For things closer to the camera, we end up with values that are not that far off from one another. But the further back we go, the numbers start going lower faster. This is exactly what we want, otherwise we will end up with a flat plane. Let's go back in Unity and plug that in the code. I'm going to continue to reuse this variable, so it's still called distance, even though this is not what this is anymore. But let's not get caught in this. So we want to define a vector that we will add to the vertex position. The only thing we want to modify is the height, or the y-axis. So let's put zeros for the other values. Now here we can plug in our very simple formula. We want to square the distance on the z-axis, so distance.z multiplied by distance.z, and we want to multiply that by minus 1. And now let's add this to the vertex position, but since we switched to world space at the beginning, we should switch back to object space. This is again a multiplication matrix provided by Unity, so we don't have to do too much. Let's save and go back to Unity. So yeah, it's working, but the curve is clearly too extreme. Let's modify that and reduce the curve by multiplying by, let's say, 0.01. And that's much better now. Okay, let's also try the same for x and see what happens. Here in the shader, where we calculate the height based on the depth, let's swap that for the width, or x. Let's click play, and we can see now that the curve is to the left and to the right of the camera. Now let's just put both of these together. Let's do distance.x squared plus distance.z squared. Going back to Unity, now we have this curve effect on all sides, so the plane feels like a sphere. We hard-coded 0.01 to reduce the curve earlier, so let's add a variable for this so it can be controlled from the editor. Up here, underscore curve, make that a float, and let's make it 0.01 by default. We also need to define it within the CG program, again float underscore curve. In our function, instead of multiplying directly by 0.01, we will multiply by underscore curve. And now back in Unity, we can control the curve from the editor. You can stop here if you want, but I have a few other fun things that I wanted to show you. First, let's go back to the shader and let's try the opposite, where the closer to the camera a vertex is, the lower it gets, and the further away it is, the higher it gets. So it curves the opposite way than the way we just had it. All we have to do is remove this -1. So back in Unity, there we go. I actually really like this. It's like we're in a giant hammock. If anyone out there is making a game about a giant hammock, this one's for you. We can see though that the shadows are a bit messed up. So what we can do is here in the pragma say add shadow, and that would tell Unity to recalculate where the shadows should appear on the screen. You don't always need to do that, only if you see some obvious problems with your shadows. And last little fun thing, let's use cosine to see what happens. This is actually turning into a very nice function visualization tool since we're applying it on a flat plane. Now in Unity, when we're moving around and therefore the camera moves, we have these waves, which is pretty cool. You can really try anything here. And if you do, please let me know in the comments if you come up with anything fun. And that's it. Thanks everyone for sticking to the end, and I hope you enjoyed it. I really enjoyed making this video, and I'll see you soon. Bye!